is going to be available for our carbonyl chemistry. Before we get into that question, let's actually break down the individual pieces. So the carbonyl is referring to just the carbon-oxygen double bond. Okay? And I intentionally left space on either end open. Okay? The reason being is that if we change the atoms out there, we get a different functional group. So for instance, if I make this a carbon and this a carbon, what functional group do I have? I now have a ketone. Okay? So it's an internal carbonyl. It's locked inside of a carbon structure. If, however, we go through and change it, where one of those carbons is now a hydrogen, what functional group do we have? We have an aldehyde. Okay, and I guess I could add this extra information. So we could say our ketone is an internal carbonyl. And yes, I've lost my pen pretty much permanently. And the aldehyde is an external carbonyl. Okay, if we were going to look at nomenclature, how would we refer to our ketones? How would our name change?
It would end with one.
We look at the ONE ending. Okay, if we were looking at an aldehyde, how does our name change? We get an al as an ending, even though the al in this case started at the beginning. Okay? So those are, for nomenclature, what we'd be applying. Okay? Could we switch between other atoms? Does it have to be carbon and hydrogen? Good answer. No, it does not. What happens if we make it an oxygen?
It still has a carbon-oxygen double bond.
In fact, I'm going to move it to the other side. We still have the carbonyl. Okay, but is it a ketone? No. Is it an aldehyde? No. So we now have a new functionality because that oxygen has been added. And now the question is, what functional group do we call this one? It was kind of a trick question because there's two answers at this point. It's not specific enough. We have to know what that oxygen is then bound to. If that oxygen is bound to a hydrogen, we have the carboxylic acid. If that atom was a carbon, what do we have? Did say it earlier, so I'll just accept it. You get an ester. Okay? So the carbonyl as a functional group or as a class, we can't really name it until we start to put in the other pieces around it. Okay? And this is where our chemistry gets a lot more complicated, a lot quicker, because what if I went back through and instead of now looking at an oxygen, I put, say, a chlorine next to it. So this was an OH, this was an OC. Okay, well, it's not any one of those now, so we get a new name. We end up calling this an acyl chloride. What if it was a nitrogen? Close. We get an amide. Okay? So carbonyls can have a large range of functional groups in which they can show up in. In Chapter 13, we're primarily concerned with our ketones and aldehydes. In Chapter 14, we can look at carboxylic acids. If you move into 16, which we won't directly get into, that's when you start to see esters and how they can affect your functionality. Acyl chlorides would also show up in 16. And amides, I believe, is also 16, and it shows up also in proteins. Okay? So there's a lot of different places these functional groups can show up. They're all based primarily around the functional group of that carbonyl. Okay? So now that we know what those individual pieces are, we could go through and try and address its reactivity. Okay? So what do you see as far as reactivity when you look at the carbonyl? Okay, we've got a pi bond. What's special about a pi bond?
Reactive.
Okay, how is it reactive? It's a source of electrons, which means we're looking at, we've got a Lewis base. What else do we have? We have a Bronsted-Lowry base, and we also have a nucleophile. Okay? Which is ultimately what we did with an alkene, the same kind of idea. Okay? Except when we looked at an alkene, it was a carbon doubly bonded to a carbon. There was really no polarity associated with that double bond. Okay? So that pi bond pretty much came out and could react whichever way it went or wanted to, and that was dependent on what it reacted with. If we go through and look at the carbonyl, has the chemistry changed ever so slightly about that pi bond? What else is the difference between an alkene and a carbonyl? We have an oxygen. What can you tell me about oxygen? It's more electronegative than carbon. So if we look at that pi bond and we look at the electrons in that pi bond, is it fair to say or treat it the exact same way that we would treat the electrons in the pi bond of the carbonyl, or sorry, a carbon-carbon double bond? No. That oxygen is going to start to draw the electron density away onto the oxygen, and what we end up seeing is a resonance structure. Okay? So we could go through and draw out that resonance structure. We'd end up using our double arrow. Our oxygen gained electrons, so it is now negative. Our carbon lost electrons, so it should now be positive. So if we go back to our definition of what we were looking at with our pi bond, okay, it's a source of electrons, Lewis base, Bronsted base, nucleophile, all that fun stuff. Okay, is it really the pi bond that has that reactivity? Or is it better described coming from the oxygen? Makes a little bit more sense to refer to the oxygen as being our Lewis base or our Bronsted base or our nucleophile, because that's where our electrons are. Okay, because it's more electronegative than that carbon. Okay? Because we now have a polarity, or because we now have a polarity with that double bond, we're going to add some extra information to this. We didn't just put the electrons on that oxygen, we also end up forcing a positive charge to form. Okay? So what's the issue with that carbon now? Well, it lacks electrons. What kind of reactivity is possible for a species that lacks electrons? It could act as an electrophile. And I heard acid, and I'm going to leave a big blank there. Lewis. Could we specify Bronsted? No, why not? Our positive charge isn't on a hydrogen atom. Okay? So what we're looking at as far as our reactivity is our carbon can now act as a pretty good electrophile. Our oxygen could act as a nucleophile, or among other things, we could look at the Bronsted base, Lewis base, all that other fun stuff. Okay? So now we've got an idea of that chemistry. So let's decide between those two, which one do we think is going to be particularly more reactive? Okay, so when we look at the carbonyl, do we say, as far as chemistry goes, it's going to react as a bronze, or as based on the oxygen, or based on the carbon? Okay. I heard a couple oxygens out there. For oxygen to react, what does it have to do? No. For it to react, it has to share its electrons. Is oxygen particularly willing to share electrons? Why not? Because it's highly electronegative. So if we're going to look at the carbonyl in our neutral state, the oxygen is already fairly happy as being neutral. And in fact, we can even draw more electrons towards it. So it's already pretty stoked. Our carbon, on the other hand, has lost electrons. So when we look at the reactivity of our carbonyl, the primary thing we end up finding out, or end up discovering about our carbonyls, is that we're looking at them act as electrophiles or Lewis acids. Okay? And it all has to come back to that carbon. Okay? So most of this chapter is based on looking at what nucleophiles can react with the carbonyl, okay, or that electrophilic carbonyl, carbon of the carbonyl. Okay, so what possible atoms could act as nucleophiles? So describe a nucleophile to me then. Let's try that. Okay, if we've got a nucleophile, you're right about charge. What charge? Negative, so it needs to be a source of electrons. Looking for a negative. Okay, is our primary source. Okay, or being a good nucleophile. Okay, what atoms could potentially act as nucleophiles? Okay, anions or negatively charged species, yep. I want to get even more specific. What atoms in particular? Halogens. Okay, so we could try and have a halogen come in and attack that carbon. Okay, the problem with that though is that we form our bond to our halogen, okay, and then we get our oxygen with our negative charge. That carbon now in the middle, what happened to its positive charge? Became even more positive. Why?
Because the other negative elements pulling.
We have two electronegative elements now pulling electron density away from it. So we may have lost the resonance positive charge, but now we have an inductive positive charge. Okay? So carbon doesn't particularly like that, and it's going to start to try and pull electrons back from one of those two groups. Which group is it going to be easiest to pull electrons from, the oxygen or the halogen? The oxygen, what ends up happening? Our electrons come back down, kick out the halogen, and no reaction. Okay? So while halogens are a good negative charge to use or think about, they end up not working out for us in this case. Okay? So what other things could be negative? Let's pick simple things first. You picked halogens because they're electronegative. What could we do with oxygen? Oxygen's also electronegative. We can make a decent nucleophile out of oxygen. How could we do that? Say if we started with water, how could I turn water into a good nucleophile? I could take away a hydrogen, make water act as an acid, and we end up with OH minus. What have we just made? Nucleophile. Do I have to have a hydrogen out there? No, it could be OR minus. Okay. If we go through and run this similar kind of chemistry, we can go through, put that OR group down here. What happens? Our electrons bounce up. What happens to our carbon? Still pretty positive. Still has two fairly electronegative elements attached to it. Doesn't particularly like that. It likes it a little bit better than our halogens, okay, but not by much. That species ends up being highly unstable and falls apart. Okay, so we can take advantage of that chemistry, which we will later on when we look at protecting groups, but it's not going to be our best nucleophile. So what other nucleophile could we potentially use? Okay, I like the option of going to sulfur except for one reason. This class was organic chemistry. Let's think simple. Sulfur is a little too big for me. So let's move to nitrogen. Okay, nitrogen works out even better than oxygen as a nucleophile. Why?
It's still electronegative, but not as electronegative.
It still has the lone pair that can act as a nucleophile, but it's not as electronegative. Okay, how can we see that in the chemistry? Oxygen can act as, or a neutral oxygen species can act as an acid and a base. So it can both share electrons and take electrons away from a hydrogen or an atom bound to it. But what happens with nitrogen? Can it act as an acid? No, it only acts as a base. It's only willing to share those electrons. Okay? So nitrogen ends up being a pretty good nucleophile for us as well. Okay? So we could go through and have nitrogen come in and attack using its lone pairs. Okay? We still have the issue of two electronegative elements being attached to that carbon, but it's at least a little bit better because, again, we're moving towards elements that are less electronegative. Okay? This species is unstable, and it does fall apart. And we'll look at that falling apart when we get to nitrogen as a nucleophile. What's the last nucleophile that we could possibly envision? As a hint, we've been moving across the top of the periodic table. We could move to carbon. But wait. Does carbon have any lone pairs to share? No. So how can we get carbon to act as a nucleophile? We have to somehow make it negative. Okay? And this is where this chemistry gets the most interesting. Okay? Because in all of the other cases, it ends up falling apart once it attacks. But once we put that carbon on, we push our electrons back up onto that oxygen, we now don't have anything electronegative to take the electrons back away from our center carbon. Okay? And in fact, if we now try to look at the electronegativity, what happened to the positive of our carbon? Well, now it only has one electronegative element attached to it. So what happened to its effective positive charge? It's reduced. We end up forming a carbon-carbon bond, okay, that sticks. So we end up generating a more stable structure. Okay, so most of this chapter is focused around these three nucleophiles and how we can apply them under different circumstances. Okay? And because I don't have any slides, I can leave it to you guys to decide. Which of these three do you want to start with? Okay, let's see. Is that what I picked? Yes, it is. So what we can go through and do is evaluate oxygen as a nucleophile and try and address what can happen here. So let's go ahead and pick, Okay, a standard carbonyl to start with. We'll pick acetone. And what I'm going to do is react it with an oxygen source. And we can look at it in a couple different mechanisms. In the first case, we'll pick a stronger nucleophile. So we'll make our oxygen as our nucleophile negative. Okay? If we make it OH, start with that. That negative wants to react with a positive. Where's our most positive atom? Okay. How many bonds would that carbon then have?
5.
Too many. So what do we have to do?
Break one.
Break a bond. What's the easiest bond to break there? Pi bond. We can push those electrons out. And we can get a tetrahedral intermediate. Drawn terribly, I might add. Okay. Is this structure particularly stable? No. There's two reasons you can give me for why not. There's charge, so let's address that one first. If I've got a negative charge, how do I stabilize that? Bring it near a positive. Okay, what positive do I want to bring it near? This is where carbonyl chemistry becomes really annoying. Probably the most positive thing would be some kind of hydrogen. Okay, so we could say there's a hydrogen source. Whoops. We'll come back to that in a second. So that hydrogen can be pulled off of some structure. I didn't draw that structure yet. I'll draw it in a second. And we can end up with this species. Okay. Where did that oxygen get that hydrogen from? From an acid. Not a bad idea. It makes sense for an oxygen to pick up a hydrogen from an acid. Except, what can you tell me about your starting material, in particular that guy right there, in green? It's a base. Huh. Well, how do we get an acid and a base in the same solution? This is where these reactions are a bit irritating. Where we're getting it from is water. In the process of putting hydroxide into the solution, we also have to put water into solution. Okay? So in this process, our water will also act as a proton source, allowing us to neutralize this reaction. Okay? And we can finalize that final product there. Okay? What would happen if instead of using, so let's go through and put it in as blue, OH minus, I used OCH3. Does our mechanism change? Not really. All we're doing is changing the hydrogen for the OH. So instead of getting our dialcohol, we can end up with this species. Which of those structures do you think is more stable? Left or right? Blue or black? Blue ends up being more stable. Why?
Because carbon is less likely to leave than hydrogen, or break off of the oxygen than hydrogen.
So what you're evaluating is the reactivity of this position. I actually didn't know the answer of this until I just asked it, so, or at least a reasonable explanation. If we look at the black structure, that hydrogen can act as what? Bronsted-Lowry acid. If we look at the blue structure, what can that CH3 act as? Nothing. Okay, it has very, very limited reactivity. Yes, it could act potentially as, what is that, an electrophile, okay, to kick out the oxygen, but that's not particularly likely. Okay? There's other chemistry available there. So that if we go through and evaluate this, if we were to decide which of these two is more than likely to occur, or which one would occur faster or higher yield, this would end up being our favorite product out of this. Okay? That CH3 is substantially more stable, okay? Which stabilizes that overall structure. Okay? Which is going to bring up the next issue of why that's important. Okay, what did we say about the carbon in each of these cases? That carbon and this carbon. When we looked at it on that last slide, did we say that carbon was particularly happy or stable? No, it wasn't. Why? There's two very electronegative elements attached to it in those oxygens. So what this oxygen could do is share its electrons back down, except then that carbon has too many bonds, and what happens? We kick off the other one, and we're right back to where we started. Okay? If we move to our other case, we still have the potential for those electrons to share back down, except now we have a CH3 to also share electrons with that oxygen. Okay? So it ends up becoming a little bit less reactive and a little bit more stable. Okay? And where this is going to become important is instead of stopping at this stage, what we're going to go through and do is take it a step further. Okay, so don't kill me. We can go through and pick a structure. This is where it's going to become important. Let's take a look at something like this. I want to be able to do the reaction where I add H2 to just the carbon double bond. Turns out that when we do addition reactions with hydrogen and say a palladium catalyst, it will add that hydrogen to every double bond. So if I tried to run this reaction, the actual product that I would get would end up looking like the alcohol. If I want to stop at that carbonyl, I have to somehow control that reductive chemistry. Okay? So I can either change the reagent, or what we can do is try and come up with some way to protect the carbonyl. Okay? So what we're going to go through and do is pick something that's reversible. Okay, well, the reaction that we just looked at got rid of the carbonyl, but then we said it was also reversible. It could go backwards. So what we're going to do is instead of going directly into H2, instead of doing this first, we're going to try something else first. And our first step is going to be to add OCH3, not quite that yet. Okay. What's special about this molecule? It's got two negatives, phrased in the context that we've been looking at as far as our oxygens. It's got two nucleophiles. Okay, so we could go through and run the reaction that we've already done. Whoops. We can take our negative charge, attack the carbonyl, push our electrons up. And the product of this reaction, we get our O negative, we get a hydrogen hanging out there. We get CH2, sorry. CH2, O minus. Yes?
What happened to the double bond?
Which double bond?
The double
Oh, thank you. Sorry, I forgot that's what I was doing. Yes? Okay. Well, our next step would be to stabilize one of those minuses. So we could go through and say that hydrogen or that oxygen picks up a hydrogen. Okay. This is where I don't particularly, or I'm not probably the greatest person to ask about these things. We could go through and put in water, or the other option is we could put in the conjugate acid of our nucleophile. Okay, which is exactly what we did last time. Pretty much the same thing. Our conjugate acid of hydroxide was water. Okay. What's the result? We get yes? I'm really going to run out of space. Okay. That carbon is still positive. Okay. Still not particularly happy. Okay. So what can happen is we can take the electrons from, say, that oxygen, because it still has those electrons. We'll say, you know what, carbon, I'll help out. I'm going to push some electrons down towards you. But then how many bonds would that carbon have? So what happens? What bond does it break?
Hydrogen?
Is hydrogen going to be willing to take electrons away from carbon?
No.
No. What bond does it break?
Oxygen.
Should not be doing it that way. And I'm going to do a rotation here. And I'm going to get rid of the, no, I'm not. CH2, CH2, O negative. And what else am I missing? Okay, what else am I missing? Hydrogen we can get away with by saying it is implied. And oxygen would be positively charged. Does oxygen want to be positively charged? No. So what's it going to want to do?